Hello. So, welcome to the class. Welcome to the next episode of the solid state physics class. So, we were discussing about CMP basics, and we discussed about the introduction and also the 2D lattices. What is lattice? What is basis? We had discussed in very short, in very brief manner. So now that we know what is a lattice and what is a basis, we can move to the real systems, because in real life, when we will be working with some materials, when we will be looking at some materials, it will not be 2D materials. 2D materials are gaining a lot of attractions, a lot of attention nowadays because of its capability, of its novel and exotic nature. But for most parts, the basic that we are going to work on will be 3D lattices. It will not be 2D lattices, but it will be 3D lattices. So it is helpful for us. Now it is the time for us to move and see and explore what are the 3D lattices, how are they, and what are the structures. Are there any special lattices? Can we work with them? Do they have special properties? There's a lot of questions to ask. So let us get started. So what is 3D lattice? It is exactly the same thing. Now it is in 3D space, not in 2D space. So there are two lattice vectors, A1 and A2, and A3 also, which is extra. A1 and A2 were there even in the 2D lattice, but A3 is extra. So now it becomes a 3D lattice where there are three primitive lattice vectors, and any vector, any point from origin to any point where there is a lattice point, the position vector will be given by a linear combination of these three vectors, where the coefficients must be positive integers. Not positive integers, they must be integers at least. They can be zero also. If all of them are zero, then it will be origin. But I mean, it can lie on some plane. It can span the whole 3D space. So it will be n1, n2, n3 are the coefficients which are integers. They can be negative also, they can be positive also, they can be zero also. Okay, so now that is fine. That is the most general description of 3D lattices. But now, how do we get more structure into it? We need to classify, we need to make more classes, we need to see the structure, underlying structure of how many lattices, how many types of lattices are possible. And actually, to be honest, there will be infinite number, infinite varieties of lattices will be possible. But we are not interested into that, all of that. We are only interested into the Bravais lattices, or these are certain kinds of 3D lattices which are found more in nature, which are found more in nature. These are more abundant in nature. So we have to ask ourselves that why are we studying all of these things? Because we want to analyze already existing materials that we see all around ourselves. Not only the materials, but specifically crystalline materials which have a well-defined lattice structure. So we are not going to be interested about everything and anything. We are going to be interested about certain kinds of lattices. So these are the Bravais lattices. There are broadly 7 different kinds of lattices which are known as Bravais lattices. And how are they changing? So it is basically the unit cell that is changing. Unit cell of different lattice structures have different properties. So that is exactly what we are going to see. So what is a unit cell? So this is a unit cell of a 3D lattice, and these are the hidden sides. So what are the lattice parameters? These are A, B, C, the length scales, and the angles between these vectors. So these are called alpha, beta, gamma. These are the angles. So there are 6 parameters through which we specify a unit cell or a lattice structure. And there are 7 different kinds of Bravais lattices where these things will be different. So let us get started about what are these things. So the first one will be simple cubic, the simplest of all. It's just a cube. It's a plain cube where all the sides are equal, a equals to b equals to c, and alpha, beta, gamma are all 90 degrees. Okay, so that is simple cubic. That is the most important and most studied, by the way. And we will going to be studying it after we have done the Bravais lattices. We have done categorizing the lattices into Bravais lattices. This simple cubic will be the most studied. Uh, just pardon me, it's a typo. So yeah, so it will be the most studied lattice structure that we will ever see. We will analyze we will add bases to this lattice, and then we will analyze how it changes, and we will do a lot of things with this. Okay, then we have tetragonal. What is tetragonal? It is like one face is square, the other face is not. So a equals to b, but it's not equal to c, but all the angles are 90 degree. It's like a parallelepiped. It's like a cuboid. It's like a cuboid where one face is a cube. Uh, so this is called tetragonal. Then we move to the next. We move to orthorhombic, where it's also a cuboid, but none of the faces are a cube. Even a equals to not equals to b, not equals to c, but all the angles are 90 degree. It's indeed a cuboid. Okay, then we move to the next. It is called rhombohedral, and so here, or it is a parallelepiped. Yes, it's a parallelepiped, but it's not the angles are equal, the sides are equal, but the angles are not 90 degree. It's not a cuboid. It has equal sides, but it is not a cuboid. Now we come to monoclinic. Monoclinic is all the sides are not equal. Alpha beta is 90, but the base where a gamma is, that is a parallelogram. The like the vertical sides might be rectangles, but the uppermost and the lowermost side will be parallelograms. They will not be rectangles because gamma is not 90 degree. Okay, then it is the last, the most unequal, the most asymmetric one. It's called the trigonal. Here, none of the angles are equal, none of the sides are equal. It's basically a kind of completely, it has no equality, it has no equality in even in angles and even in the sides. And the last one, what we want to see is the hexagonal lattice. What is it? It is like the base is a rhombus with gamma equals to 120 degree, and the alpha and beta are 90 degree. It's a rectangle. The vertical sides are rectangle. As you can see, this can be represented as a part of a hexagon. Hexagon, it's like a hexagonal kind of like a prism. It's like a prism where the sides are hexagons that can be divided into three such lattices, three hexagonal lattices. So this is a very interesting thing. Uh, so you can actually do something like this. So yeah, so we can extend this actually. So let me use a different ink. We can extend this. Yes, just like that, we can extend this. So we can also draw similar stuff in the upper portion also. And it's just like that, we can create a complete, like repeating lattice basis system. Lattice system, not, we have not added basis yet. So we can just create a repeating lattice system by this. So as you can see, we have already created 4 such lattices, and it fits into the hexagonal structure really well. So we can also like describe the lattice points. Let's say there is a lattice point here. Yeah, there is a lattice point here. There is a lattice point here. There is a lattice point here, 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 here. So these lattice points are all part of the hexagonal lattice system that we are seeing. And all of this can be represented also as a hexagon. It's like the hexagons and the centroid of hexagon. Same can be done for the lower part. Here also we can create this lattice points. Okay, so these are the all the Bravais lattices, and now we know there are 7 types of Bravais lattices: simple cubic, sorry, simple cubic, tetragonal, orthorhombic. These all are cuboids. This is a cube. Simple cubic is a cube. Then we have rhombohedral. We have monoclinic. We have triclinic. And finally, we have hexagonal. These are the 7 structures. This is the most asymmetric. This is still okay. This is a parallelepiped. These are parallelepipeds. So triclinic is also a parallelepiped, but it's highly asymmetric. So yeah, so these are all the things that we have. Now we will, this is all about lattice. This is about lattice, 3D lattice, not about basis. This is not about basis, this is about lattice. Now we will add basis to these lattices, but we will only consider simple cubic because other structures are not that much studied. I mean, at least in our course, simple cubic does describe a lot of materials, lot as in a lot. So simple cubic is very successful in describing a lot of materials, a lot of structures, a lot of lattices in real life materials. So we will stick to simple cubic in this simple course, in this basic course. There can be study of the other lattice structures, and these are also pretty like widespread. Okay, so now we look at the simple cubic lattice. So, okay, so now if we add, let's say, at the center point where all the diagonals meet, if you add one atom or one lattice point, not lattice point, one atom, one basis basically. So, if we do that, then what we get is very simple. It's called a simple cubic lattice. So, like simple cubic lattice is already there, and we add one uh, basis point in the center where all the diagonals meet, then it's called a body centered cubic system. So it's like simple cubic lattice plus one point at the center. Center, what do I mean by center? Center is meant, I mean by center where all the diagonals meet. That is what I mean. Okay, so it is thought to be a basis of atoms at 0, 0, 0 and half, half, half with a simple cubic lattice. Why so? Why aren't we considering all the other stuff, all the other points? Why are we only considering this and this? Why are we not considering other points? So we are only considering this and this because if you think about it, if you think about what we are how do we describe a lattice basis system, and you will see that if we start to translate it, this blue system, the blue balls connected with the blue string. So if we start to translate this according to the simple cubic lattice vectors, which are what? Which are ai cap, aj cap, and ak cap. If we start to translate this system by these vectors infinitely, I mean, as in ai cap, 2 ai cap, 3 ai cap, in the same in the j and k direction, or the y and z direction. If we try to do the same thing, then we will recover this exactly the structure that I am talking about, where you will also recover the orange atoms, because these orange atoms will be, I mean, they will be attached to something else. They will be attached to a center atom of in some other unit cell. But we will eventually recover this. Uh, okay, so yeah, so we will all recover all this, because let's say, for example, this atom, this lattice point will be connected to another lattice point in the adjacent unit cell. This will be connected, this lattice point will be connected to some other basis point or other point in the above unit cell. So like that, if we keep translating this system, then we will recover the whole body centered cubic structure that we have shown in this figure. So okay, so now let us go further. Yeah, so now we see what is R corner. R corner is just n1, n2, n3. These are the lattice points, and our center will be n1, n2, n3 plus half, half, half. So n1, n2, n3 can be any integer. Okay, so now what we do? Now we see the plan view. What is a plan view? Plan view is like you are seeing it from the above. Here we can see that from above it obviously looks like a square, one unit cell, and the center atom, center point, as you can see, it is there is a by 2 written under it. Why? Because it is at depth a by 2. So this is the plan view. This is this is like a convention or a system of views. So the primitive lattice vectors, they are what? 1 0 0 0 1 0 and half, half, half. Why so? I mean, it's like basically the x-axis, the y-axis, and the half, half, half. Because this creates the whole system. So how to see this? It's like a primitive lattice vectors. What is primitive lattice vectors? It makes a primitive lattice, primitive unit cell. And what is a primitive unit cell? The cell which has only one unit and only one point inside it. So that is called a primitive unit cell. So if we can see, so let me draw it. Okay, so just wait. Yeah. So if we draw it, if we draw this, and then we draw the different, yeah. So now we also draw, yes. So now we also have the lattice points So there is the center lattice point, there is another lattice point here, 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 here. We draw all the lattice points. Okay, so now the primitive lattice vectors are given by this, this, and this. If you see what is being happening here, then you will see if you extrapolate this into this direction. If you make an lattice vector just like that, if you make a parallel piped like this, let's say, and you so here there will be another lattice point, obviously. So let me draw that. It will be the center of the next the unit cell of the BCC unit cell just at the right. So this will be the mm, another point. So if you do the same thing with this, it will connect to another, and this will connect to this will connect to some other, they will connect, they will connect, they will connect. So it is like this kind of a lattice vector on a unit cell basically. So as you can see, there are 8 atoms at corners of the unit cell. So like okay, let me actually denote the unit cells of the other. So these blue atoms, these blue points, are not a part of this BCC unit cell, but these are rather the parts of other BCC unit cell. It's like this, the 1, 2, and 3. These points. Now, one point is at the BCC unit cell, which is just at the right of the present BCC unit cell, which is depicted by the dark blue lines. The number 3 is just behind it, and number 2 is like a diagonal kind of thing. It's like the 1 and 3, it's behind 1 and at the right of 3. So like that basically. So if you see this green primitive unit cell, it's the primitive unit cell. So how many atoms does it have? How many total net atoms? It is 1. Why? It is 8 atoms, but each of the atoms is shared by 8 unit cells. So it is 8 into 1 by 8, which is 1. So as we can see, this primitive unit cell only has one uh, one cell, one point, one lattice point, or one basis point, whatever you say, inside it. So that's the basic definition of primitive unit cell, and that's why the primitive lattice vectors are given by as given a1, a2, a3, 1 0 0 0 1 0, half half half. You can also I mean, it is a convention, but you can also do 1 0 0 0 0 1 half half half, or 1 0 1 0 0 0 1 half half half, as in xy, not only xy but yz or xz. But xy and half 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 is the convention which is being followed, so it is better to follow that. Okay, so every point in the 3D space can be written as a linear combination of these vectors. So when we summarize this, then what we get is, this is the BCC unit cell, numbers of atoms in unit cell. The BCC unit cell is 2, because BCC unit cell is not the primitive unit cell. The BCC unit cell is given by the blue cell, the primitive unit cell is given by the green cell. The BCC, if you see, it has how many atoms? It has 8 atoms in the sides, the red atoms. So it is 8 into 1 by 8. Each atom is shared by 8 other unit cells, and in the center there is another 1. So it is 2. In one blue unit cell, there will be 2 atoms. In one green unit cell, there will be only 1 atom. Only 1 point, not atom, but 1 point. Okay, so the generalized coordinates are given by r corner and r center, as you can see, and the primitive lattice vectors are given by 1 0 0 0 1 0 and half half half. Okay, so now we can create the Wegener site cells of the BCC also. How to create that? As you can see, you can create it by drawing the bisecting planes of different atoms, And just like that, I have taken this from the famous book by Simons. So this pictures have been taken from there, and these are the Wigner-side cells of BCC, as you can see. So it has some rhombus looking like sides, and it has also hexagon like sides. And as you can see in the right side, they join together seamlessly to make up the whole 3D space. Okay, so let us move into the next portion, that is the face centered cubic. And what is that? It is basically a simple cubic lattice structure with a lattice point, as you can see the blue points at the lattice points, and also it has green points which are at the center of the faces of the cube. So it is like a simple cubic with a basis of atoms at 0, 0, 0, half of 0, half, 0, half, 0, half, half. So it's like the basis is given as this. This is the basis, this is a part of the basis, this is a part of the basis, this is a part of the basis, and this is a part of the basis. This four. Mhm. So these four are constructing the FCC lattice, and as you can see, just like the previous case, if you translate this through the lattice system, if you translate this whole system to this point, let's say to this point, then you will again see that there will be, you see this, you see this. If you just translate, keep translating it, then you will recover this FCC unit cell structure. So these are the simple cubic bases of atoms with simple cubic lattice of atoms with basis at these 4 points, as you can see. And in the plan view again, we can see that if you look, then we will see 4 points at depths of a by 2 at the faces basically. So that is the plan view. Okay, so now there can be in the body centered cubic there were only two types of atoms. One is the corner atom and one is the center atom. Now there will be four types of atoms. What are these? Center at corner atoms N1, N2, N3, XY, so midpoint of the XY phase, that will be adding one half half 0, midpoint of YZ phase 0 half half, midpoint of XZ phase half 0 half. So we can add these things and get new points in the vector. And the primitive lattice vectors are given by this. Just like BCC, we can create a primitive unit cell. So let me try to create it. It might get clumsy, but let me try at least to uh, create this. Yeah, so yeah, this is the unit cell. These are the primitive vectors, and if you just extrapolate this, then you will get uh, yeah, so you will get this will move to this. This phase is complete. This will move to this, and this will move to this. So there might be a little bit clumsiness here. So let me see. Yeah, so it's basically face center to face center here, face center to face center, face center to face center, face center to face center, then that to corner. And same thing, it is like three faces like that. And again, three faces like that. This face center to face center, face center to corner. Yeah, so it will be like that. Here, let me draw the points actually to distinguish. This is a corner point, this is a corner point, this is face center 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 point, and these are also face center point. So these are the six face centered points of the FCC lattice. And as you can again see that this primitive unit cell will only have one point effectively. So the primitive unit cell, the green cell is the primitive unit cell that has only one atom. But the red cell, that is the FCC, actually the simple cubic lattice with a basis, that has four atoms. You can easily see that. At corner there are 8 atoms shared between 8 unit cells, so 8 into 1 by 8, and there are 6 in the face centers, which are shared by 2 at 2 unit cells, so 6 into half, 3, 1 plus 3, 4, and the generalized coordinates are given by this, the primitive lattice vectors are given by this, and similar to the BCC or the body center cubic, we can create a Wigner-Seitz cell of the FCC lattice just by creating the bisecting planes and joining them into a polyhedron. And again we can see that these are joining each other to make the whole 3D plane. So what we studied today, so this is all for today. This is a so it is very important to so the most important point that I would say in this whole lesson was to differentiate between the FCC unit cell and the primitive unit cell, similarly the BCC unit cell and the primitive unit cell. And given the primitive lattice vectors, you should be able to clearly draw the primitive unit cell from the given lattice vectors and say that yes, why it is a primitive unit cell, because it only has on one net effectively it has only one atom or one point inside it. So this is the red cell is the FCC unit cell, green cell is the uh, primitive unit cell. Similarly, if we do for BCC, if we go to BCC, then we will have uh, yeah, so we will have the blue unit cell is the BCC unit cell, the green unit cell is the primitive unit cell, and again the primitive unit cell only has one point in it. BCC cell has 2 points in it, FCC has 4 points in it, but in both the cases, primitive unit cell by definition will only have 1 point in it. So that is the main thing that we learned today. We learned about 3D lattice structures, we learned about Bravais lattices, and mostly what are the Bravais lattices are the most general categorizations of 3D lattices. And then we looked into the simple cubic and we added some basis, and we saw how the Wigner-Seitz cell looks, how the primitive lattice cells looks, how to primitive unit cell look, how the primitive lattice vectors look, and what are the properties, because BCC and FCC are one of the most universal and one of the most widespread structures that are ever possible in nature. And so when we will move to reciprocal space, when we will move to how to make reciprocal space formalisms for all of these things, then we will see that these are very important. These are very important, these two structures, and these structures are interchangeable also in reciprocal space to real space. These things, when we will see, it will become clearer. And so this is all that we did. So we have completed with the basic understanding of 3D lattices. And so yeah, that is all for the classes. So meet you in the next class. Thank you.